I am Seongil from KAIST, and this is a joint work with my colleagues Trung, Nguyen, Jihwan, Ben Stock, and my advisor, Sooel. Today I'm going to talk about our research on differential testing to find browser bugs in content security policy enforcement. So it's not working. Okay. So cross-site scripting XXS attacks are known to be one of the influential web attacks. If arbitrary JavaScript code crafted by an attacker reaches the browser due to a vulnerable web application, the attacker will be able to execute malicious JS code with the vulnerable web server origin. To prevent these attacks, there is a security mitigation specified in the response called CISPA. Especially the browser refers and enforces a defined CSP to block the execution of the malicious JS code. CSP is a widely used security mechanism. In 2020, about 480,000 unique CSPs were used per day. So now, let me briefly explain how CSP works. First, site operators refer to the given CSP specification and write their own policies to protect their pages. And similarly, browser developers also refer to the same spec and implement their browser so that it can correctly enforce a defined CSP. Here, our research question is what happens when developers misunderstand or misimplement the CSP specification. So let's see an example. According to the spec, inline scripts should be blocked by default. However, developers misunderstand that inline scripts should be allowed by default. Then, developers implemented their browser with this incorrect point of view. As a result, they introduced the bugs to their browser. And we call these bugs as CSP enforcement bugs. As a consequence of these bugs, the browser enables the adversary to bypass certain CSPs and execute malicious JS code, contrary to the expected behavior of the defined policy. There have been previous studies on finding insecure CSP deployment or misconfiguration from site operators, but they didn't consider to find CSP enforcement bugs existing in browsers. And note that there is one previous work on finding these bugs, but they manually crafted each testing input leaving many corner cases unexplored. So our ultimate goal is to find these bugs, especially related to JS execution, which is the original goal of the CSP protection. So how can we systematically find these bugs? First, it is important to generate diverse set of inputs that may trigger CSP enforcement bugs. Especially, we should generate a comprehensive set of CSP and HTML. The second challenge is related to implementing bug oracles. So to clarify this challenge, let's assume that we have these large number of testing input. Then, for each testing pair, we need to match the corresponding spec, define the correct behavior, and convert this behavior into a testing oracle. And this manual identification of correct behaviors for each testing input is not scalable and error-prone. So, and finally, let's assume that we have these 4 million cases that causing the bug. Now, developers need to analyze these huge number of cases to identify root causes, which takes a lot of time. In summary, these are the challenges in finding CSP enforcement bugs: generating diverse inputs, implementing bug oracles, and identifying root causes. So the key question for our work is that, is there any testing tool that can efficiently handle all these challenges? So to answer this question, we propose here our framework, DiffCSP, which is a differential testing tool that can find the CSP enforcement bugs. So our design goal is to overcome all the challenges I mentioned before. So I will explain how we handle them. First, in order to generate diverse set of inputs, we use the grammar-based input generation. Especially we referenced known CISP enforcement bugs, XSS payloads, and the ECMAScript specification and the HTML cheat sheet in deriving on HTML grammar to generate testing input. And note that our references include diverse ways of executing JS snippets. For example, we can correct these two different ways of executing JS snippets from each reference. Then we can prepare, from these references, we can prepare the grammar. So to generate more diverse patterns, especially all known forms of executing JS calls. So for example, to prepare this grammar, we can extract one of the JS code that appends on HTML instance. And for the HTML grammar, we can extract iframes on the event handler. In this way, we can prepare the grammar and we can generate, after that, we can generate diverse set of inputs by deriving this grammar to generate about 26,000 HTML instances that may trigger the inherent bugs. And for regarding CSP generation, we prepared representative CSP directives and values and combined them to generate about 1,000 policies. And to address the second challenge about implementing bug oracles, we leverage a differential testing across multiple browsers. Especially, our intuition is that the burden of defining the corrective behaviors has already been addressed by each browser with their perspective on the spec. And with that, they implemented their browser. However, let's assume that Safari developers misunderstood the CSP spec and implemented their browser with this incorrect point of view. If so, when the same input is given to each browser, the results will be exist, and if their result is different, we can specify that we found a possible abnormal behavior related to CSP enforcement. So in summary, using the differential testing, we can avoid the need to model the correct behavior for each test input. And finally, to identify the causes for the large number of inconsistent results, we use the decision tree with a set of conditions. And to identify the causes for these 4 million inconsistencies, we can think we need to cluster similar results together. However, with the traditional clustering algorithm, it is difficult to understand under what conditions each group was clustered, making it difficult to analyze root causes. So our suggestion is to leverage a decision tree to cluster the results. Especially, we can train a decision tree so that similar results would belong to the same leaf node to form clusters. Then, we can get the decision boundary due to the set of conditions leading to each classification decision. So, therefore, it is possible to analyze root causes by identifying these set of human readable conditions in the decision paths. So for the training of this tree, we labeled each test result as consistent or inconsistent. And using the components of the test input as features, we trained a decision tree used for root cause analysis. And with this approach, we could reduce huge amount of results to only 525 paths in the decision tree to pinpoint root causes. So now, let me briefly explain how we conduct root cause analysis with this decision tree and one of the inconsistent results. So we can see that inconsistencies occurred when the script SRC directive is existing in the policy, and the unsafe inline keyword is not existing in the policy, and finally, the inline script is existing in the HTML snippet. So in this way, we can analyze the root causes with the set of human readable conditions. So this is how DiffCSP works. Now I will show experimental evaluations on our system. So we tested a total of 8 browsers, including 3 desktop and 5 mobile browsers. And we noticed that browser engines control the CSP enforcement behaviors. So we compared the inconsistent results between the 3 browser engines. And first, we evaluate the efficiency in terms of finding CSP enforcement bugs. So our system found 37 bugs in 3 browser engines with 27 security bugs. Here, security bug means the bug that allows the adversary to bypass certain CSPs and execute malicious JS code. And we reported these security bugs to their corresponding vendors, and 23 of them were patched at the time of writing. Especially, Google rewarded with $4,000 for the bugs found in Chromium. And we further categorized the root causes of the found bugs into 10 groups. And we note that most bugs allow the adversary to inject arbitrary JS code. Now, let's take a look at these 2 categories. So first study is related to non-ignored CSP values. So according to the spec, the keyword unsafe inline should be ignored when strict dynamic is specified. So when this HTML is served with this CSP, the keyword unsafe inline should be ignored because of the strict dynamic, and the inline script attack should be blocked by default. However, we found that Chromium-based browsers do not ignore the keyword unsafe inline and enable the execution of the malicious inline script. And note that the keyword strict dynamic is newly introduced in CSP level 3, and many bugs were caused by these new features of CSP level 3. And we can learn that as CSP spec evolves, the number of directives and values increases, and complicating the description of the spec, which could lead to more browser bugs. And at the same time, this increasing complexity in CSPs requires systematic browser testing. And the second case study is related to incorrect CSP inheritance. According to the spec, documents from local schemes should inherit the CSP of their parent page. So for example, in the given HTML instance, since the frame navigates to one of the local schemes, JavaScript column page, it should inherit the parent page's CSP. However, with this subtly different HTML instance, we found a bug. Especially, the adversary leveraged the existing iframe's location. Especially, she can attach the event handler so that it can dynamically redirect it to the local scheme page. And according to the spec, this frame should inherit the parent page's CSP. So we could expect that only nonce-based scripts, nonce-protected scripts are allowed, and inline script without nonce should be blocked. However, we found that Safari didn't inherit a parent page's CSP, allowing the execution of the malicious JS code. And we observed that 28% of the bugs were caused by these kinds of dynamic page redirection. And we note that developers should carefully implement CSP inheritance, especially when this kinds of dynamic redirection occurs. And despite our result, our system has some points to improve. So due to the fundamental limitation of the differential testing, our system cannot find the bugs if all the browsers exhibit the same bug. And it will be interesting research direction to automatically extract correct behavior, enabling the single browser implementation, single browser testing. And we acknowledge that our grammar is not complete to generate all possible HTML forms. So we support extending our grammar by adding new derivation rules. And Finally, we will open our source code on GitHub to boost future research. So if you want to utilize our framework, please visit our repository. And conclusion, we proposed the DiffCSP, a differential testing tool, to find the CSP enforcement bugs. We take 3 approaches: grammar-based input generation, differential testing as a bug oracle, and decision tree-based root cause analysis. And we found 29 security bugs and 8 functional bugs. So that's all of the presentation. With that, thank you very much, and I'll be happy to take any questions.
So the title is called DiffCSP, and you say you're going to use the grammar to generate the different HTML files, right? Do you think about to take some algorithms or any feedback to keep generating more queries, like retrieve more coverage and find more bugs, like the very hot fuzzy topics?
Yes. So we can extend the grammar by, so if we see any other patterns of JS execution or HTML ones, we can just add that components to the grammar by symbolizing the HTML or JS parts.
Okay. So that's the thing you're proposing is a solution to solve this problem?
Yes.
So any feedback would be helpful to generate more interesting test cases?
Actually, this our version have not feedback, but actually, so using the feedback, so leveraging feedback to generate more comprehensive input is really interesting.
Okay, thank you. Do you have more questions from the audience? Okay, don't blame me. I'm going to ask another one. So you are going to open source this work. So you mentioned you find a bunch of bugs, but after you finish this work, does anyone else use your work to find more bugs? Because currently you are generation based. You generate, if I remember correctly, 25,000 HTMLs, right? Are you able to generate more to find more bugs? Or you or others use your tool to find more bugs?
Yes, we open our source code. Actually, we current version of grammar find only 39 words, but after adding new kinds of HTMLs, actually I don't know about adding more direct patterns, we can find more words.
Okay. Yeah, hopefully more people are going to use your work and find more bugs and improve the security on CISPA. So last call, we have more question? Yes, okay. Finally.
What other type of application classes could this work be applied to? Instead of just browsers, they could maybe security modules for SE Linux or Berkeley packet filters or something like that.
So I put on this session.
Are there other application classes that this technique would work on besides browsers, libraries, or security frameworks that take in some kind of policy and
so other policies checks.
Other areas in computer systems besides browsers.
Other areas.
Mm-hmm.
So you mean that our approach can apply to other area? Or?
Yeah.
Maybe yes. So so what is the other area? So for example, other security policy or?
Yeah, so for example, maybe firewalls, where firewalls define a particular security policy and then add exceptions to those security policies. And then they then enforce, dropping or accepting of a packet based on these complex security policy definitions.
Yes, this also can be used other rules. Actually, the intention of the testing case should be changed to bypass an area. And actually, differential testing is used. We propose the differential testing to to avoid the need to model the complex spec. So if that area has some kinds of complex spec, then the area can be actually use differential testing.
Okay, thank you.